Rucking places a unique demand on our respiratory system. One, we're bearing load, and two, that load is actually sitting and restricting the thoracic structures. And so this is a really good study in the European Journal of Applied Physiology that was done back in 2016 by Phillips and his team, and they wanted to quantify the ventilatory response to prolonged exercise with heavy load carriage. And so I wanted to dive into that study with you here today and a little bit of the outcomes. I think it's pretty unique. So what did they do? They took 15 men, 15 quote healthy men, and they had them do two different iterations on a treadmill. They did a 45-minute walk without load. They did a 45-minute walk with load, specifically a 25 kilogram backpack, so a decent load. And obviously we know that walking with load is going to be harder, so they measured oxygen consumption and adjusted the pace on the loaded walk so that the oxygen consumption met that of their unloaded walk. So ideally, that was their attempt to control the variables of muscle fatigue and muscle strain that come along with that loaded walk, ideally to isolate the respiratory system itself. Obviously, limitation to the study here is that they only used 15 subjects and they were all men. So we're kind of extrapolating some of this data to women and to other folks, younger children, older individuals. And so take that with a grain of salt. Regardless, they measured these 6 variables here. I'll define them on the next slide, but breathing frequency, minute ventilation, tidal volume, end inspiratory lung volumes, and the maximum inspiratory and expiratory pressures. So what are those? Breathing frequency is how many breaths per minute. The minute ventilation is the total volume moved per minute. And so that's actually a function of breathing frequency. And the next variable here, tidal volume. So tidal volume is how much volume of air I move per breath. So every time I breathe in and out, what is the volume of air? Breathing frequency is how many times do you do that a minute. And so ideally, your minute ventilation is the multiplication of those two. So here you have minute ventilation is equal to the tidal volume times the breathing frequency, and that's the total volume of air that you're moving in and out of your lungs in 1 minute. That's your minute ventilation. Your end inspiratory lung volume is the amount of air left in your lungs after an inspiration. So how much air is sitting there as I change to expiration. And then you have your pressures, right? So maximum inspiratory pressures is the force of inspiration, and expiratory is the force of expiration. And that is more of a function of the actual strength of the diaphragm, which we know drives respiration, the strength of your intercostal muscles and all those things. And a little bit about muscle fatigue is kind of, I think, why they isolated that variable. And we'll talk a little bit about some of, what the actual data shows. So what are the outcomes with these variables? So with the 25 kilogram load, they noticed the following: that your breathing frequency increased by 22%. So that means that you're breathing 22% more times per minute. The minute ventilation went up by 15%. So the amount of time, the total volume of air, rather, that you're moving in and out of your lungs per minute went up by 15%, which would make sense, right? If you're breathing more often, you would imagine that your total volume of air moved in and out of your lungs in a minute would go up. However, notice that they didn't go up to the same degree. So you know that if minute ventilation didn't increase to the same degree that breathing frequency did, this is our equation here, you know that it had to come at the expense of a lower tidal volume. And so that makes sense here, where we see our tidal volume dropped by 6%. So what does these 3 variables mean? So when these folks were loaded, they were breathing more often, but they were taking shallower breaths. And so the amount of extra work that they were doing to take more breaths was not correlating to the same degree of increased air movement, because ideally that's what you want. You need to move more air per minute, so you have more gas exchange. You're blowing off more CO2, more of those metabolic waste products, and also getting that oxygen that you need. And so that's a really key point of the study, and we'll talk about some of the physiological implications of that here in a second. Keep going down the list here. End inspiratory lung volumes, those were reduced. Sorry, I didn't put that in here. They were reduced by about 6%. So imagine in the 25 kilogram load group, you take your full inspiration, you were limited by less than 6% to the normal. So ideally, you're not taking as big of a breath when you're under load, and that's probably due to some of that mechanical restriction from the actual load on the thorax itself. Maximum inspiratory pressure, so that's the amount of pressure that you measure when you take that inspiration. How much are you able to drive with your diaphragm, with your intercostal muscles to expand the rib cage, and that also decrease. And that shows a little bit of respiratory muscle fatigue under load, right? It's a strength exercise. It becomes a strength exercise. Remember that inspiration here, if I look at the breathing process, inspiration involves the diaphragm flattening and the ribs expanding, and that creates a larger space within the thorax to drive pressure and air into the lungs. So we really need good, strong diaphragm and intercostal muscles to create a strong maximum inspiratory pressure, and so that goes down when you're under load, just like anything would go down under load, right? You can do more push-ups unweighted versus weighted. The maximum expiratory pressure, that was unchanged, and that makes sense, right? You actually have a lot of extrinsic thoracic pressure from this load that you're carrying, and so ideally when you exhale or expire, that's actually going to be compressing your rib cage, and it's going to keep that expiratory pressure maintained. And so back to kind of these big physiologic changes here, I just want to talk about what does that actually mean. So what is the impact of tidal volume, of a decreased tidal volume and an increased breathing frequency? So there's this concept of dead space in respiratory physiology, and dead space means if this is a view of the right lung, right, an anatomical perspective, this will be on the right side. Here is our the voice box here and our larynx. And so all of the air that comes through our mouth, down our trachea, down the bronchus, and then bronchioles, all of this is called dead space, right? There is no gas exchange until it gets to the distal aspects of those airways, which is in the actual lung parenchyma itself. So you have to move a considerable amount of air to even allow for gas exchange to occur. And if your amount of air that you're breathing per breath is decreasing, then you're actually not going to have as effective of gas exchange. And so you end up just moving air kind of in these areas that are called dead space, and you don't get good gas exchange. And so what ends up happening is in order to adjust for that, you breathe a little bit more, and you start to retain a little bit of carbon dioxide, and it actually signals to your body more respiratory distress, more increased demand that actually might be not to the same degree of the metabolic demand that your body is placing on you. So we're actually seeing a increased perception of pain and discomfort that is increased compared to the actual pain and discomfort of the demand of the rucking itself. And that is because of our change in respiratory physiology. So what do we get from this? One, I think it's important to have really good customization of your equipment. Make sure your equipment fits your body, is optimizing you for the best respiratory mechanics, right? You don't want to be restricted more than you need to be, because all that's going to do is place load on your respiratory system. And two, recognizing this and making a conscious effort to overcome these natural drops in tidal volume and natural increases in breathing frequency that maybe we can overcome just by actually maybe thinking about it more and being more deliberate with our breathing when we're rucking. So this is just a really good example of some of those changes from that, I think mostly the external pressure of the ruck and load itself on our thoracic cavity, and understanding that this is going to impact our perception of the ruck itself. It's going to change our mental state regarding how much we're enjoying it, and actually it's going to change our ability to make coherent decisions, right? Because at the end of the day, if you're military, you want to be able to make good decisions, tactical decisions, educated decisions that are unbiased and has nothing to do with your physical limitations. And then for other folks, you want to enjoy your rucks. So I think this is a really good study. It helps us understand the physiology of our respiratory system a little bit better, and especially under load. So hope this helps. If you have any questions, throw them down into the comments. If not, have a good rest of your day. Take care.